All right, so this will be our second installment, or actually maybe the third one, for the applications of derivatives. All right, so these are all the big theorems. All right, so the first thing I want to talk about is continuity and differentiability. All right, so determine whether this function is differentiable at x equals 2. All right, before you can be differentiable, you have to be continuous. So do we remember, which we've already talked about this year as a review, we talked about what are the 3 steps to determine that this function is continuous. All right, step number 1, f of 2 has to exist. All right, so if I look over here, we have equality here where x equals 2. So when I plug a 2 in here, 2 squared is 4 times 3 is 12. So f of 2 does exist, it's 12. All right, step number 2. Step number 2 is our limit as x approaches 2, because that's where the break is, and that's what we're doing, x is approaching 2, of the function has to exist. All right, so does our limit here exist? Well, the limit less than, this is the left side, greater than, this is the right side. All right, so does our left-sided limit equal our right-sided limit? So now let's plug a 2 into both of these and see if we get the same thing. So our left-sided limit, we already know is 12 because that was the equality side as well. So that's 12. Now when I put a 2 into the right side, do I get 12 as well? So 2 cubed is 8 plus 4 is also 12. Well, yeah, there we go. So the limit exists and it is 12. All right. Now the third thing, does our f of 2 equal our limit for the function as x approaches 2? So does our limit is our limit, which exists, does it equal the function value? Yep, they were both 12. So yes, so that means we have a continuous function. All right, so it is continuous. So now is this function differentiable? So how do you do differentiable? Well, you do the exact same thing, but you do the same 3 steps on the derivative. So let's do the derivative of this function. So the derivative of this function, f prime of x, the derivative is going to be 6x for the top equation and 3x squared for the bottom equation. All right, and these domains are still true. All right, so the derivative of the top equation is 6x. The derivative of the bottom equation is 3x squared. So now I'm going to do the same 3 steps for the derivative. So step number 1, does f prime of 2 exist? All right, does f prime of 2 exist? Well, equality was in the top row. So if I plug a 2 in here, I'm going to get the answer 12. And that's a quinky dink, that's 12 again, but oh well. All right, so when I plug a 2 in here, 6 times 2 is 12. So yes, it exists, f prime of 2, I do get a 12. All right, step 2. Now I want to know, what about the limit as x approaches 2 for f prime? All right, does f prime have a limit? So now we need to do our left-sided limit and our right-sided limit. We plug 2 into both of them and see if we're going to get the same answer. So we already know this is 12 when I plug a 2 in there. So when I plug a 2 in here, 2 squared is 4 times 3, I also get 12. So yes, the limit is 12. And then step 3, does f prime of 2 equal the limit of f prime of x as x approaches 2? Are those the same? And yes, they are. So that means we are differentiable as well. So this problem is differentiable because the derivative is continuous. That's what that means. To be differentiable means that your derivative is continuous. All right, so there's an example of continuity and differentiability. And to be differentiable, you have to check the continuity first, because you can't be differentiable if you're not continuous everywhere. All right, so that's the review on that. All right, the next big theorem I want to talk about is the extreme value theorem. The extreme value theorem says that if we have a continuous function on a closed interval from A to B, then we have to have a min and a max. And this is the little picture where we drew different drawings of when you got a max and when you have a min. All right, so no matter what my function looks like, whether I've got this and it goes down to here, this has a max, this has a min, and it has to be a continuous function. All right, I could even draw it going straight across. All right, going straight across, there is a max and a min, but the max and the min are the same. All right, so it's okay for your maximum and your minimum to be the exact same thing. That's okay. All right. So no matter what kind of function you draw here, all right, no matter what type of function you draw, it will always, as long as you draw a continuous function, it will have a maximum and a minimum value somewhere. So if you have a continuous function on a closed interval, you have to have a minimum, you have to have a maximum. That is the EBT theorem. All right, so now let's do an example of EBT. Okay, now EBT says, okay, that we have to have a max and a min. So I should be able to find the extrema on this closed interval for this function. So how do I do that? Well, I'm going to use the first derivative. So I'm going to do my derivative, f prime of x equals, so my derivative is negative 2x plus 3, all right, negative 2x plus 3. And I need to just set this equal to 0 and look for undefined. These will be my critical numbers. So when I set this equal to 0, I'll get negative 2x equals negative 3. So then x equals divided by negative 2 will give me 1.5. So there's my critical number. Now, I have to make a test. So when I taught you last time, or last year, I taught you to make a table. So we need to put all of our critical numbers in here. And then we're going to plug them into our function to see who wins. So I'm going to plug in my endpoints and my critical number I found to see who wins the race. So whoever's the highest will be the maximum, whoever's the lowest is a min. So we're guaranteed to have a max and a min because this function that I have is a continuous function. So I just have to use my derivative because all of these things we're reviewing are applications of your derivative. So we took our derivative to find any critical numbers that are in the middle, somewhere between 0 and 3. And then we also use our endpoints because one of your endpoints could be your max or your min. All right, so now I'm going to plug these in. So if I plug 0 in, I get 0. If I plug 1.5 in, what do I get here? 1.5 in there will be 4.5 minus 1.5 squared is 2.25. So that'll be 2.25. And then plugging a 3 in here. If I plug a 3 in there, I'm going to get 0 because that'll be negative 9 plus 9. All right, so that means this is my maximum, and I have two minimums. All right, so that means it depends on the what and the where. So what is your minimum is 0. Where is your minimum? Well, I have one minimum when x is 0, and the other minimum is when x is 3. So it depends on the what and the where question. So what is your maximum? Our maximum is 2.25. Where does that occur? That occurs when x is 1.5. So it depends on the question, where and what. So this is the where, and this is the what. So what is our min is 0. Where is the x coordinate? What is our maximum is the y value. Where is the x coordinate? So that's your EBT. All right, and then we did IVT. And this is the one y'all had struggles with all the time because you couldn't remember this little sentence. All right, if f of x is continuous on a closed interval and k falls in between f of a and f of b, then there exists a number c in the interval such that f of c equals k. All right, and this is a picture. Here's your function. It's continuous on the interval a to b. And between f of b and f of a, because you put b in the function, get this number, put a in the function, get this value, f of a. So somewhere between these y values, there's some number k. And if we go out from there and hit the function and come down, there'll be a c value in between a and b that'll give you that k value that falls in between f of a and f of b. So as long as we know that our k value is in between f of a and f of b, we're guaranteed that there's some number in the interval that will give us that y value of k. That's the intermediate value theorem. And when I introduced this in class last year, I talked about when I was born and how tall I am now and when was I ever 4'1", and the answer is yes. because I'm now taller than 4'1", and when I was born, I was shorter than 4'1", and your growth is a continuous function. So that means at some point in my life, I had to be 4.1. So that's what intermediate value theorem is. All right, so let's do an intermediate value theorem problem. Verify that the IVT applies to the indicated interval. Find the value of C. All right, so the only condition that had to be met is this has to be continuous. All right, so that's what the theorem said back here. If f of x is a continuous function, all right, so that's the only thing that has to be true here. So do we have a continuous function? Yes. This is a polynomial, it's a parabola, so this is a continuous function. So the next thing I need to check is my f of a and my f of b to see if they're to see what they are, because I'm trying to find a c value to equal 11. So I have to make sure that when I plug these numbers in, when I get f of 0 and f of 5, that 11 falls in between these answers. All right, so let's put a 0 in here. We're going to get -1. Put a 5 in there. We're going to get 25 plus 5 is 30, minus 1 is 29. And yes, indeed, 11 falls in there. So here's where we have to write that little sentence. Since f of x is continuous and 11 falls in between -1 and 29, then by IVT, there exists a C in the interval 0 to 5 such that f of C will equal 11. So there's your little sentence. All right. Now, this also says find the value of C. Well, the way you're going to find the value of C is you're just going to set this function equal to 11. So if I did x squared plus x minus 1 equals 11, so then that would give me x squared plus x, and then I subtract 11 gives me minus 12, and then I factor, so that's 4 and 3, and it'll be more positive, so positive and negative. So my two solutions are -4 and +3. And notice +3 falls within the interval. So there's the answer that we were guaranteed by IVT. All right. So by IVT, you're guaranteed that there's some C value in your interval where you're going to get 11. So I just set the equation equal to 11 and found that that answers 3, and that indeed is in this interval. So that's intermediate value theorem. Make sure you work on memorizing that little sentence again. And the very last big theorem I want to talk about is the mean value theorem. Now, the mean value theorem, there are two things that you have to have as a condition. You have to be continuous and you have to be differentiable. Then you're going to be guaranteed that there is a tangent line parallel to your secant line. So this is your tangent line. Oh, it's already written on there. That's your tangent line, and this is your secant line. All right. So this was our function. All right. So there's a secant line joining the endpoints of my interval. Then here's my function going along. This secant line has some slope, which old-fashioned slope, f of b minus f of a over b minus a, that's the slope of this line. I'm guaranteed that there's a tangent line parallel to that secant line. So that means having the same slope. So that means my derivative has to equal the slope of the secant line. So if you think about this, this is I rock equals a rock. So this is instantaneous rate of change using the derivative, and this is your average rate of change using slope. So mean value theorem is I rock equals a rock. All right. But before you can start, you have to have a continuous function and a differentiable function in order for this to be true. All right. There has to be a C in the interval so that there's a tangent line parallel if you're continuous and differentiable. All right. So take a look at this last little problem here just to review mean value theorem. Determine whether the mean value theorem can be applied to f on the closed interval a to b. And if it can, find all values of C in the open interval such that this is true. So the first thing I have to check is f of x continuous? So f of x is continuous because x squared is a polynomial, that's a parabola, and it's also differentiable because the derivative of this is 2x, and that's a continuous function as well. So f of x is both continuous and differentiable, so the mean value theorem applies. So we're good to go. So that means this thing holds true, okay? Now, so what this says is my derivative, so the derivative of this function, which would be 2x, is going to be equal to f of b. So f of b, this is a and b here. So that would be f of 1 minus f of a, and f of a is negative 2, divided by b minus a, so that'd be 1 minus negative 2. 1 minus negative 2. All right, so basically I'm just doing slope. So if I did these as ordered pairs, negative 2 and 1, all right, these are my x coordinates, so I'd put them in here. So negative 2 squared is 4, and 1, put them 1 in there, 1 squared is 1. So basically that's what I'm doing. I'm doing slope. All right, so this is my derivative on this side, 2x. And then over here is slope. So f of 1 is 1. That's where you put 1 in the function. 1 minus f of negative 2 is the y coordinate for negative 2, putting negative 2 in here, so that'd be 4, minus the difference in my x's, 1 minus negative 2. So that's just doing slope. y2 minus y1 over x2 minus x1. That's all I'm doing. So 2x equals negative 3 over 3, which is negative 1. And so when you divide by 2, x is negative 1/2. All right? So that means x is negative 1/2. So find all values of c in the open interval such that this is true. So I'm finding that this is the x value. Notice that falls in the interval from negative 2 to 1. And that's all I'm doing. I'm just finding, which I could have left it a c instead of putting an x value. All right, I put x instead of c, but I could have said 2c and made it a c, so c would be negative 1/2. All right, but this is the value that I found, negative 1/2, which falls in the interval, and I'm guaranteed that there is a tangent line parallel to the secant line at negative 1/2 when x is negative 1/2 for this function. All right, now what is the slope of that line? Well, this is the slope right there. The slope of that line is negative 1. So at the coordinate x equals negative 1/2, there's a tangent line with a slope of negative 1. Okay? So if I wanted to write that equation, I could if I wanted to, because there's my slope, here's my x coordinate. To find my y coordinate, I'd plug it into this equation. All right? And that would be like 1/4. So I could find the equation of the line if I wanted to. But mean value theorem just finds any x coordinate where your tangent line is parallel to the secant line, where I rock is equal to a rock. So in this problem, it happened at negative 1/2, which is in the interval. So that's your mean value theorem. So you also have a big handout that I made for you all. It's posted on in the lessons. But if you came and got your textbook, it's in that packet. There is a nice big chart that shows all the big theorems of differentiation and all the different, things that you need, and a picture and information about each one. So it has a lot of cool information there that I gave you. So do some practice problems and do some work on those practice assignments that I gave you for applications of derivatives.